In today's video, we shall be looking at another important analysis. So today's analysis will be based on a pulley system that is attached to an inclined plane. So our target here is to ascertain the tension on the strings that are holding the masses, and at the same time eventually find the acceleration in the system. So stay with me on this. Let's run the analysis. So from the diagram, you can see we are going to make one assumption. So we are going to assume, so assuming, so we're going to assuming no friction. So for now, let's start with making an assumption, no friction. So pay attention so that we can analyze this for future problem solutions. So let's say, so we are assuming no friction. Now, if you observe this diagram very well, you will notice that from the direction of the arrow, it's evident that M2 is greater than M1. So that makes sense. You can see M2 is heading this way and it's going to pull M1 with it. So our target is to derive the equation that is going on M1, the equation that is happening on M2, as the case may be, in order to find the tension. So for us to ascertain this, the first thing we're going to do is to draw the free body diagram for each of the masses so that we can see the forces that are acting on it. So that's the first step. So let's start with this simple one. Let's start with M2. So you can see M2. This is M2 with a tension. So you can agree with me that according to this, we can see that the forces that are acting on M2 are as follows. The first one is the weight. And evidently, we can see that the weight is pulling M2 downward. It's even as a result of how heavy the weight of M2 is, that is kind of pulling almost everything down with it. So the weight is going down. And we can also see the tension, that's the thread or the string that is attached to the mass, making serious effort to stop M2 from dragging everybody down. But it's not making enough effort. But we know that the effort is there. We can recognize it, that tension is acting upward. So understanding how the forces are acting, their direction will help you here. Now we can see that regardless of the tension pulling the force upward, the force eventually drag everybody down. So the resultant effects produced by these two forces are heading downward. That's the resultant effect. So if we put this together, we can see that in the whole system, that the greater force here in the system here is the weight of M2. So we can see that if we want to know what the resultant effect will look like, we will simply need to subtract the tension from the weight. So we say the weight minus the tension, because the weight is pulling downward and the tension is going up. So if we want to see the resultant effect of these two guys, just subtract the tension from the weight, we can see the equivalent force that is being used to push this mass M2 downward. So, and that is what I can call the resultant effect. So if we expand on this, we can see weight is mass times gravity. So the mass we're dealing with is M2 times gravity minus the tension force T, and that will give us the resultant effect, which is the mass M2 multiplied by the acceleration in the system. So that's the rate at which the object is accelerating down the hill. So if we make T the tension, the solid formula, we can see that the tension, you can see that this is M2 gravity. So if we put this guy in here, we have minus M2 multiplied by acceleration, and this is equal to the tension. So this is the tension that is acting on the mass M2. We can call this our equation 1. So you can take note of that. That's our equation 1. So moving on, let's examine the forces that are acting on M1. So this is M1 hooked up this way. So we have the first force that is acting, which we call the tension, and we can obviously see how the tension is acting. The tension is pulling this way. This is the tension pulling the whole system this way. Now, we also need to find an equivalent force that's also acting this way. So we can see, according to the forces, there has to be in opposite direction to each other. So this tension force that is pulling this way is trying to overcome the weight component that is pulling this mass this way. So which component of the weight is pulling the mass this way? So the weight component that is pulling the mass this way is what we want to find out. And to ascertain the weight component that is pulling the mass this way, we need to find out how many all the weight component that are acting on this mass M1. And they include, we know the normal weight force is acting downward. And there exists two weight components, one acting horizontally at the angle, which is equal to the angle of inclination, and the other one acting this way. And the one we are interested in is this particular weight force, this one. And we already know that this one here is given as the weight cos theta, because that's where the angle is formed. And this one down here is given as the weight sine theta. So, and this is the one we are looking for, because it is these two that are in conflict. So the tension force is trying to pull this mass up the inclined plane. And then this particular weight component is trying to drag the mass down the inclined plane. So the power tussle, and who eventually won? The tension. And we need to find the fraction that the tension used to win this, this power tussle of a thing. So what did he use? So we can establish that the whole pulling process ended up dragging the entire mass up the hill. So that's the direction of the resultant effect. So if we put everything together, we can see that the weight component dragging it this way, we need to subtract that from the tension. So we subtract that. What's the weight component? It is W sine theta. So if you subtract that, that will give us the resultant effect, which is given as the mass multiplied by the acceleration. Or let me just write it. The resultant effect R, which will give us the resultant effect R. So if we expand on that, we'll have T minus the weight here is M1 multiplied by gravity sine theta, and that is equal to the resultant effect is M1 multiplied by the acceleration. So if we make the tension here the subject of the formula, we can see that the tension is going to be equal to M1 multiplied by the acceleration plus M1 G sine theta. So this becomes our equation. So this becomes our equation 2 in the whole process. So this is the equation 2. So we are there. So this gives us the tension that is acting on the two sides of this system. So we can see the tension that is acting on mass M2, and we can see the tension that is acting on mass M1. So if you have a problem, they give you a question, let's say you are given the mass, let's say M1 is 20 kilogram and M2 is 30 kilogram, and you're asked to find the tension on the string, on the strings that is holding them. You just play around with the two equation. You use equation 1 to find the tension, assuming that acceleration is given and gravity is given and all those things. So now let's combine the equation and get the acceleration of the system. Because we believe that from the diagram, you can see that a system is accelerating. So we need to find the acceleration in the system. So to find the acceleration, we are going to combine the two equations. So let's go ahead and do that. So I'm going to wipe this part. Okay, so let's combine the two equations. So the first equation is telling us what the T tension is, and since the tension has to remain the same if the object is accelerating, so if we equate the two tension in order to find the acceleration, we will be able to see something this way. We can see that if I substitute this, if I substitute the tension in equation 1 inside equation 2, we're going to have that M2G minus M2A is equal to M1A plus M1G sine theta. Good. So now let's collect the like terms for the A. So we're going to have M2G bringing over minus M1G sine theta. That will give me, that's equal to M1A plus M2A. So if we factor out the acceleration, we will have M2G minus M1G sine theta. This is equal to, factor out A, all into M1 plus M2. So on that note, we can make the acceleration of the formula by dividing both sides by the coefficient. So divided by M1 plus M2, divide everything over there by m1 plus m2. So when we do that, we will have, if you divide this, you have your acceleration as, so let me go ahead and write that. So my acceleration will then become equal to m2g minus m1g sine theta divided by m1 plus m2. So this is the acceleration in the system. Now, which makes sense because come to think of it, we know that force is mass times acceleration. And if you're going to find acceleration, you just simply need to divide by mass. So we can attest that um, acceleration is force over mass. And in this situation, m2 is higher than m1, which means if I am to find the acceleration of the system, I just need to subtract the lesser mass from the bigger mass, that's the lesser weight or the lesser force from the bigger force, in order and dividing it by the two masses in order to ascertain what's going on. You got it, m2 is higher than m1. That explains why the weight of m2 was used to subtract the weight of m1. So you can see m1 weight minus m2 weight divided by the two masses gives us the acceleration in the system. So these three equations are very important for a system involving mass on an inclined plane with a pulley on it. So feel free to tell me what the equation will look like if m1 is not the one that is higher than m2. So I believe if m1 is higher than m2, the reverse process will be taking place, meaning that m1 will be the one dragging the system. So we'll be having the arrow facing the other way around. So I want you to work on that and let's see what the result will look like. So give that a shot. Let's see what you have.